Calculus! This is AP Calculus, Lesson 5-9, Definite Integral Rules. Here we are on our unit guide. That's our old units. There's our unit guide, 5-9. We are on our very last lesson of the unit, which means coming back on Monday, we have self-check 5.1, 5.2. Tuesday, Thursday, Friday is our fix-up, which means Monday of next week, you have a whole week and a day until our Unit 5 test. And just as a reminder, we don't have a final or a midterm, whatever you want to call it, for AP Calculus. We're just going to go right on through and teach during that time of the final. So I think we get 2 hours for the final. We'll probably get 2 lessons done that day. It'll be cool. Definite integral review. All right, so if I have a constant function, 4, and I'm taking the definite integral from 0 to 3, what is that algebraically? And then we're going to do it graphically. This is just reviewing. So algebraically, this turns into what?
4x.
Yep, took the antiderivative, evaluation bar.
0 on the bottom, 3 on top.
From 0 to 3, perfect. Which turns into?
So it'd be 12 minus 0.
Yep, 12 minus 0,
So it'd be 12.
which is 12. There it is. Bada boom, bada dang. So we know it's 12. Let's see if our graph matches that picture. All right, so someone aside from Rochelle, how do I graph that?
Draw y equals 4.
Draw y equals 4.
Fill in the distance between, fill in the area between that and the x-axis between 0 and 3.
All right, so between 0 right here and between 3 right here. And then we can shade that just by going chunk, 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 chunk. And finding the area, how do I do that? We'll give it an arrow.
Finding the area. Well, it's already basic shape, so you just find the area.
Which is?
Multiply base times height, or height times width, something similar.
Yeah, base times height, sure. If you want to do it that way.
So 12 again.
12, cool. We got 12, we got 12. Good, good, good. So, by the way, we need to know this formula because it's well, we don't need to know it, but it would be a nice formula to know. I'll be referring to it later for some shortcuts. So, whenever I have an integral from 0 to 3, I assume that the beginning is 0, the end is 3. So, I'm going to say a general integral from a to b. That means that general integral from a to b will be the following formula, and that's why I gave some room up here, which is this. That integral will be, you do b minus a, the end minus the start, and then you multiply that by whatever constant you're given, so by whatever number you're given. So for this example, 3 minus 0, the end minus the start was 3. 3 times that 4 was 12. We don't have to actually do the antiderivative. We don't have to plug in 3 and 0. There's your shortcut right there. Short, sweet, simple. It's kind of nice. Do we all see? Well, it always works with constant functions. So if you just have a number, then it works. So far so good. We understand why that's the case. All right. Linear. So linear just means we have some line. My line is x. Let's go ahead and do this without using the graph. This is going to be equal to?
X squared over 2.
There it is, x squared over 2.
And then 0 through with the line.
Evaluation bar from 0 to 3. All right. That turns into?
9 over 2 minus 0.
Yep, and therefore it's just 9 over 2, which is 4.5. You can box that one. Let's see if that matches our graph. How do I graph that?
You have to plug in the line for the slope.
Yep, what is the slope of that guy?
It'd be
1. Y-intercept is 0. So y-intercept, bang, slope, go right 1, up 1, like that. All right, so there is my graph. Why does it do that? That's what I want to know. Huh, interesting. If I erase it, does it go where? Oh, weird. Okay. Then what do I do next?
Then you plug in from 0 to 3.
From 0 to 3? I'm not really plugging anything.
Well, I mean, as in,
Shade.
yeah.
Shade in between 0 and 3, so I'm going to make a little bar that goes right here so I know where I'm shading. So I'm shading this area right here. And that area right there, I do the square. That's, well, it is a square in this case. Normally I should always refer to this as a rectangle, so I'm never incorrect. This is a rectangle. 3 by 3, which means this rectangle has an area of, well, the square, the rectangle has an area of 9. And then once you take it in half because it's divided in half, then you do get 4.5. Or 9 halves. Same answer, which is equal to 9 halves. So far so good. This is easy peasy review. Quadratic. We haven't seen one of these quite yet, but let's check it out. So, x squared. Graphing x squared. Let's just, oh wait, I don't know why I'm skipping a step.
I have a question.
Yes.
For the linear, would there be a way to find it faster? Just like a constant?
Sadly, no, because antiderivatives are all over the place with these guys. Yeah, I wish there was, but yeah, you have to do it this way. You do have to take the antiderivative. This is the only one that has a shortcut that I know of. Quadratic. Antiderivative of x squared is
1/3 x to the third.
1/3 x to the third. Between 0 and 3. Plug those in, you get 9. Arrow, Rochelle, do we agree it's 9? Yep, because it's 27 divided by 3, and then 0 for the second half. Good. All right, let's go ahead and do the graph now. A cool little graph. So we know that x squared has its vertex, its very lowest point, where? Say it louder. 0, 0, 0. Yeah, the origin. And then we know that if I plug in 1 for x, if I come over here to the x coordinate of 1, 1 squared is 1, which means I come up here to 1. If I plug in 2 for x, I get 4, so plug in 2, I get 4. If I plug in 3, I get 9. And I know that a quadratic is curvy. So I'm going to do my best to make a curve through it. All right. And again, I'm finding the area between 0 and 3. I'm always doing that for all of these. So between 0 and 3, that means I'm going to go like this, choink, and shade in the area that we're looking for. Looks like that. All right, how am I going to find that area?
Could it be that it's 1/3 the area of the rectangle?
That's a good guess, but the trouble is, what would happen if this was 1/2 x squared or 1/3 x squared? How would that change your formula?
It would have been x squared is x cubed.
That's not, maybe I need to explain in words, so, or with writing. So if I had 1/3 x squared versus, I don't know why I'm writing so sloppy, x squared versus 1/2 x squared, how does that change the formula for this guy? We don't really know how curvy it is, and I'll just,
Isn't it x cubed?
I mean, it is when we take the antiderivative, but we're just looking at the graphical representation of x squared right now. Ben thought that if we looked at this rectangle, then you just do 1/3, but I'm saying, well, I might change this to a curve that looks like this, that's slightly more curvy or less curvy. So how would that change the formula? And I'm going to stop teasing you guys. You can't do this. It's impossible to do. This is the reason why we invented calculus. So graphically,
So you just do it algebraically.
you can only do it algebraically. Do a sad face. Can't do it graphically. But I'll show you what you can do. Let's look at the other part. So this fourth part on the right. If I'm evaluating between 0 and 3, let's go ahead and shade this in a very special way. Well, I guess you don't really have colors, but I have colors, so I'm going to do it in a very special way. I'm going to say that green is positive. So I'm going to shade this in green and this in green.
Can we use color pencil?
You want color pencils? I have them in here if you want to grab them. And I'm going to do yellow for negative. I don't like red for negative because they look basically the same to me. I can tell you overall if this area is positive or negative. Can you see it too? Is it more positive or is it more negative?
More positive.
Yeah, it's more positive. Positive answer.
So that's the only answer?
Yeah, that's all I'm looking for. I just want you to know that this, if I take that integral, I know that I'm going to get a positive answer.
Is it because there's only two positives and one negative?
That's not quite it. It's just kind of eyeballing, and I say, okay, if I add up that area in my mind, add up that area in my mind, I could still have 3 negative areas and 2 positive areas, but if the 2 positive areas are much, much larger than those small negative areas, it could still be a positive answer if there's more of these negatives.
So like say like there's 10 of little small negatives and it's just one positive that big. Would it be just a positive answer?
If there were 10 of these and just one of these, it would probably be a negative answer if there were 10 of these. That's quite a bit of area. Yeah, it's really hard to estimate area. Practice makes perfect, though. It's just working on your eyeballing. All right, but today's lesson is the backside, definite integral rules. Some of these you have seen, some of them you'll be formally learning. Yeah, and this is going to conclude all of our notes. This is exciting. So if I have the integral from the same point to the same point for the bounds, what do you think that this is going to be equal to? From the same point to the same point.
Would it just be
Zero.
away?
F of A, 0, I don't know. We need a tiebreaker.
Well, if it's just from A to A, then it's a line. So isn't the area of a line 0?
You agree with 0? Okay, we have 2 people say 0, so I'll go with 0, and that is correct. And then the notes I'm going to write here on the side, what's actually happening, just so you can look back at this in half a year, you'll be like, oh yeah, that's what happened. This is when the start and end at same point. All right. We have seen this rule number 2 before. This rule number 2 is when I have k, I'm always assuming that k is a constant. If you want to write that out on the side notes, k is a constant. And if you...
For constant.
I know. Maybe I should use the octothorpe, the hashtag. I don't know what would be... Maybe I can improve the notes a little bit, but I'm going to say that k is a constant. What I can do if k is being multiplied by a function is I can pop it outside of the integral. So I can say that this is the same thing as k times the integral from a to b of that original function, f of x. And then we have to multiply it by that thickness, dx. So in words, what we're doing here, if you're multiplying by the constant, if multiply by a constant, pull out, come on now, pull out of integral. All right. This one we have definitely seen before. If I have something to the power of 1 right here, I can do what with this integral?
Distribute.
Yeah, go ahead and distribute that integral. And I actually do like having that representation of distribution to help us remember. And I did plus or minus because it goes both ways. So let's go ahead and write the rule here. This is equal to the integral from a to b of f of x dx, plus or minus whatever one you started with. It doesn't switch, it's the same sign. The integral from the same bounds, a to b, of that other function, g of x dx. And I guess the only word that we really need here is distribute. Distribute. And it's only if you have to the power of 1. If you have to the power of 2, then you have to be doing something with powerhouse, reverse powerhouse, stuff like that. Then you'll have an inner, it gets messy. All right. On to number 4. This guy. Ooh, this is weird. Normally it goes from A to B, but now it's going from B to A. How can we switch this? So what I'm trying to say here, and we haven't really seen this before, but what I'm trying to say is what if you have an integral from like 5 to 3? That's weird. Normally we should have an integral from 3 to 5. So the order has been reversed here. We need to get it into the correct order. So this is the same thing as negative integral a to b of whatever function you have, f of x dx. Let's write down that formula and then just sit back and appreciate how nice that is and what it actually means. So graphically what's happening here, and maybe I can look at the graph up here, if I had the integral from 3 to 0, instead of going from left to right, it's basically saying go backwards from 3 to 0. So when you go backwards in terms of the integral down here, that means you're actually having negative area. So in order to make it forwards, just assume that it was negative. So if ever you have these bounds out of order, know that you're going to have another negative multiplying by that entire function. All right, so the notes that I want for the side for this is if you need to flip the start and the end, so we'll do like a little arrow here connecting the start and end. If you need to switch these, that implies that's negative. And if you don't like that symbol, I can write negative here as well. All right, and then number 5, and we have seen this one before, and this one goes forwards and backwards. So I'm going to do immediately right now, I'm going to do an arrow this way to the left and an arrow to the right. It goes forwards and backwards. You can split it up or you can join them up. If I go from A to C, and C is our suspect point, and then I go from C to B, that means you can actually combine these two functions together to say that they are the integral from A to where? It was from A to C.
A to B.
Yeah, but now it goes, yeah, exactly. A to B of that same function, f of x dx. You can glue them together.
What happened if it wasn't just f of x? Like,
F of x and g of
say,
x,
Yeah.
then you can't really do anything because it's not the same function. Then it's just two different integrals and you evaluate them. Yeah, so the sum of two segments adds to one large segment, and then if you go backwards, one large segment gets broken up into two segments. And that's from our piecewise formula that we saw yesterday in 5-8. Cool, those are all 5 of the really key rules when I'm taking integrals. It's funny that I teach you the formal rules on the very last lesson. We've been learning these informally, and now there's a very formal way to do all of these. Any questions? All right, that concludes the notes. Go ahead and write your summaries, please.